Okay.
Right. So welcome everyone to our life science session today on infrageometry. I wanted to give you some updates and flesh out some of the concepts that we sketched out last time, mostly to do with duality and what we call shapes that I think are interesting, geometry-like objects finally showing up in our pre-geometric or infrageometric context. So thanks, Dugan, James, and Nick for being here today, and good to see some of our viewers. And yep, without further ado, let me share my notebook here. Okay, so of course, all of you are aware of infrageometry. The goal here is to use this discrete combinatorial structures, we're calling hypergraphs, as replacements for topological spaces in what normally one could think of as continuous geometry, or the standard academic notion of differential geometry, and so on. The basic idea is that one has a collection of finite collection of locations, abstract locations, the nodes of a hypergraph, and some information about the connectivity between them, and mainly what we call a betweenness information. So the fact whether there's space that can be traversed between different locations. So when you look at what we're calling a spatial hypergraph, which for now could be any random hypergraph like that, then you should be thinking about that sort of abstract model of space.
Can we do 150% zoom, Carlos?
Yep. How about that?
I'm just looking at the stream. Yeah, maybe one more notch. Yeah.
Hypergraph like that. Oops.
There we go. Yeah, that is good.
Yeah, I think this is better. So yeah, that's the basic idea, and the technical question that we're trying to solve here is how do we actually recover a mathematical or computational structure that resembles differential geometry and algebra, as in manifolds, tensor fields, calculus, connections, all that kind of stuff. So our main interest here is perhaps today we want to talk about shapes. So I want to explain the distinction between the terms sort of shape and why are we using the word shape that typically doesn't get used in mathematics. The reason is precisely that we in infrageometry we have a notion that doesn't really exist in continuous geometry, and that notion is basically the raw material that everything is made of, which is hypergraphs, right? So when you look at classical geometry, and this is Euclidean geometry, when people were literally drawing on a piece of paper or like on a blackboard, and then abstracting away from those substrates, the notion of a chunk of space is always well defined, right? Like you have a notion of subspace or submanifold that is always well defined, and in a way you always have a natural notion that applies to the whole of your space, but also to chunks of your space. Now, in our context, that is also true at a naive level because we have nodes and we have edges. So in some sense, edges are just collections of nodes. So in some sense, everything are edges. And so, your sub pieces are just edges at the end of the day. But the intuition here is that infrageometry is an infrastructure that builds on top of discrete informational structures, and a behavior like geometry or a behavior like algebra emerges from the sort of machine code level or the very noisy and complicated combinatorial level. Therefore, the notion of a shape, the notion of something that has a well-defined geometric entity, like would be whatever, a triangle or a sphere or something like that in classical geometry for us, has to be properly defined. It is not given for free. The reason, and the best way to illustrate this is to comment on how adjacency works in this spatial graphs, and how we're understanding the betweenness relations between nodes. So focus on the middle edge here, sort of this central hyperedge in this hypergraph. Note that we have 3 nodes, right? In blue, these are what we call vertex places for redundancy, just to emphasize that they are actual locations. And there's a edge between these 3, and then there's another edge between these 2, right? So each of these edges carry what we call an edge place appropriately, which is indicating that there is space between these points. So the reason why this particular case that is on the screen is not geometric in the usual sense, so this doesn't correspond to a shape that we could intuit as you know, humans familiar with usual geometry, is that how could it be that there is space between each of these nodes, but there's no space between some pairs of these nodes, and there is some space between a pair of these nodes? This is wholly counterintuitive. This is sort of non-geometric, right? That does never happen in our space, right? In our basic intuitions of space. So what's happening here is that what I would say is that there is a notion of space, but there's no notion of shape. Right? There's no notion of integrated space, so to speak, right? There's notion of something being somewhere and something being next to something, but there's no notion of all those things being in a cohesive relationship where they're all part of a sort of an underlying space matrix, so to speak, or like fluid, right? Or fabric, perhaps. So that would be you know, that would be defined in terms of exactly this notion of betweenness. So to make things more concrete, and I'll probably come back to neighborhoods here in a sec, but to make things more concrete, I want to talk about yeah, shapes and simpliciality. I mean, I guess it could have come directly to this point, and apologies for this because this dictionary is not very mathematically literate. So the idea here is, you know, if we have something like a surface like this, let me just run it. Oops, I need to combine edge places. Where's edge places? I think edge places. It's here. Let me just run this few functions. All right, yeah, this should all be running. Okay, make sure that we don't crash the notebook just by loading visual stuff. Okay, let's load the multi-vector so that everything's ready. So I should have done this earlier. Right. So we'll run this now. Yeah, we should get that. So what is happening here? What's happening here is that this looks like a triangle, right? This is a faithful, as far as my understanding goes in infrageometry right now, this is a faithful representation of a triangle, because we have 3 locations in space, and we have all the information, all the betweenness information that we could ever claim in, say, I want to say Euclidean space, but actually it could be any topological space, right? Which is that if you have a statement that tells you that between 2 points there is space, and then there's a third point between which there's also space, then there's space between all of them, right? So this is a property that I call simpliciality, right? So simpliciality is this notion that when you have a hole, and you gap it, so you sort of void it, you leave a gap, but there's something in the boundary, right? So a simplicial complex, as many of you might know it from geometry, has to do with this sort of interlocking structures where, you know, lower dimensional faces are always induced from the higher dimensional faces. So simpliciality here in this very primitive context of just spatial graphs and spatial hypergraphs is the notion that if you have a high arity edge, then all the lower arity edges must be included, right? So to the degree of which this is the case, that's the simpliciality of your hypergraph. So a shape would be a subset of these hyperedges that has a full simpliciality, right? So in this case, this is a triangle, right? This is to me a well-defined triangle. So if you wanted to do, for example, an infravolume, I would define it as, so just use this as, so now I would have 3 points, right? Oh, sorry, this is actually not, that's not the vertex list. So I will now have 4 points. I'll just declare it for clarity. So this is like defining a tetrahedron, a chunk of volume. And so we go back one by one. We're not including the unary edges. I mean, maybe there should be there just for redundancy, but they don't add much in the visual way. So I'm just omitting the unary ones. So the main edge here is, I'm going to put it at the top, is the quaternary one. And so if we have the quaternary one, we should add all the lower dimensional ones. So let's do it step by step, maybe. So we first start with this, right? So that's a chunk of space. I mean, you can imagine it being a sort of filled volume with a tetrahedron shape. Now we need to include all the faces, right? We need to include all the, so this is a 3-dimensional chunk, a tetrahedron, and we need to include all the 2-dimensional faces of the tetrahedron. So there's 4 of them, right? So we're gonna do basically any 3 vertices, take out 1. So I'll do 1, 2, 3. I'll do 2, 3, 4. I'll do 1, 3, 4. And I'll do where's it missing? 2, 3, 4, right? Nope. It 1, 2, 4. That's the one. Right? So now I included all the 3-dimensional, quote unquote, 3-dimensional surfaces on the sides. And then finally, you just need to include all the 1-dimensional sides, right? So again, these are all the possible binary edges. So 2, 3. Again, there's 4 of them. 4. There is 3, 4. Wait, no, there's 6 of them. What am I saying? It's 1, 3. And there is 1, 4. And so now it's maybe visually a bit easier to imagine that this is a tetrahedron, right? It has a filled-in volume, so there's a quaternary edge that's filling it in, and it has a ternary edge per 3-node subset, and then it has a binary edge per each 2-node subset, right? So this we could call an infravolume, right? This is like a chunk of actual volume in space, right? But maybe there is a little bit more to the story than just that. So, okay, that seems intuitive enough that okay, we have filled space. That's fine, but you know, shapes normally have some orientation. They can be put into space. They can be transformed and, you know, operated on. So the idea is you might want to consider also the multivectors at each vertex. So let me go back to multivectors for a second. By the way, do you have any comments or pushbacks at this point? Like, do you have a strong feeling that no, that shouldn't be the elementary notion of volume in our system? Like, that's wrong.
That makes sense. I mean, this is directly in line with simplicial complexes.
Yeah. It's basically rediscovering simplicial complexes with hypergraphs. It's not rocket science, right? It's really simple stuff.
What is a simplicial complex?
Right. So we shouldn't define the whole thing because that's a technical mathematical definition, but essentially, let me just bring up, maybe as good as just a sec. I'll just bring up oh, of course, I'm not sharing the screen. Let me reshare. What? For some reason I can't see the meeting controls.
Press Alt.
Oh yeah.
Are
They were in a different screen. So let me just share the actual screen. So as you can see, I mean, I'm using the Wikipedia article because it's a very good reference for this kind of stuff. It's really thoroughly explained. But a simplicial complex is basically the discrete version of an oriented manifold, right? So you have each simplex, which is this basically these chunks of space, like intervals and triangles and tetrahedra and so on, that triangulate your larger spaces. So they do so in not just as sort of chunks, but they have internal orientation, right? So they interlock with each other. So so the best way to think about this is that if you have a triangle that is an oriented surface, meaning that there's a sense of what is up and what is down in that triangle, which you can think of like your right hand rule or something. Like you have your triangle in your hand and you're grabbing it, and so there's a thumb pointing up. That means that the surface has an orientation, right? It has some side is up and some side is down. So if you take the boundary of that surface, that orientation gets translated as not just a set of 3 lines, but a set of 3 arrows, right? Like that orientation gets induced as a circulation orientation in those 3 lines, right? So you only claim that a triangle of arrows can be a boundary of an oriented surface if they have the right orientations, each of the individual triangles. And the right orientation basically means that head needs to go into tail, right? So each arrow needs to be head into tail, head into tail, head into tail. And so you can actually go 1 dimension lower and then apply the boundary operator to the actual sides. And so you get that each arrow is made of a head and an arrow. So if you just look at the geometric entities, those are just points, right? They're just 0-dimensional simplices, right? Like they're just single points, but they are more than single points. They are signed single points. One is positive, the other is negative. So the same point can be acting as a positive orientation or a negative orientation, because it can be the head point of an arrow or the tail point of an arrow. So that's a simplicial complex. Basically, it's the formal notion mathematically that accounts for all that combinatorial structure that intuitively just connects with orientation of space.
Well, so each piece of the simplicial complex is a simplex, basically. A point, a line, a triangle, a tetrahedron, a pentatope, and on and on. So it's a simplex is sort of the simplest unit of volume for each of these dimension of spaces, and a complex of simplices is sort of taking a bunch of simplexes and stitching them together, gluing them along their boundary components, such that, let's say, you might have two tetrahedrons that are glued along a common edge or a common triangle. But yeah, so there are rules of you can't like stitch, this triangle to this triangle along half their half an edge. Like they have to share a complete edge if they share anything at all. So that's kind of the idea about the rules about how they're stitched together. And it should be noted that each simplex is oriented, and the boundary components of each simplex inherit the orientation that's given to its thing that it's a part of. But you can stitch together, for instance, you can stitch together triangles and glue them up in a certain way so as to make a Mobius band. Right, so you can make non-orientable complexes. Let's say, higher, complicated structures that aren't orientable, but each piece is individually.
Okay,
Right.
that makes sense. Okay, thank you.
So simplicial complexes in a way are the most, if some random mathematical graduate, just sort of stumbles upon our live stream, jumps in and sees this kind of stuff, and infrageometry, we're trying to define geometry and spaces with discrete things. The first thing that will come to mind is simplicial complexes, because that's exactly what these things were invented for, right? So these things were invented for combinatorial techniques to be applied to algebraic topology, right? So you can actually compute with finite linear algebra calculations Betti numbers and dimensions of homology for any arbitrary orientable surfaces, right? Like you just given the surface, make sure that a triangulation captures the topology faithfully, and then you just, your triangulation is going to be finite, because that's what a triangulation is, unless your surface is infinite in some non-cardinality sense. And then you just apply this sort of a combinatorial formula that they're essentially counting incoming, outgoing, oriented faces and so on, and you just implement it there in that way. So it's a very powerful thing. It is constantly used in computer graphics and in algorithms for rendering, especially 3D entities. But the point I want to make here is we need in our setting, orientation is something that needs to be defined in a declared way, right? Like it's not given for free. It's very similar to orientation in actual geometry. So that's where I'm going to with shapes, right? A shape is something that can be given an orientation. It's not necessarily oriented per se, but it can be given an orientation. It can be given a choice of orientation. So basically, what I'm thinking about is in the concept of multivectors. So let me just explain very briefly how we define multivectors. Although I think in the last live stream we covered it. Let me just very quickly cover it here. Let me collapse these things. So the most important notion is the notion of a neighborhood. So in our context of infrageometry right now, we have a natural definition of maybe an infraneighborhood. So each node, which is our purported bit of space, is surrounded by bits of non-space or interstitial space, right? So that structure is what defines a neighborhood, right? Like, or perhaps an infinitesimal neighborhood, but that's a very long name, so maybe I just call it a neighborhood. So for example, given our spatial hypergraph, you can just move around in different vertices, and you can see how different neighborhoods appear. So for example, this one, it's a very central. Oops. this one, yeah, this very central node has all these in the vicinity. So you have a, you know, a 5-node edge, right? So anyway, this is the basic notion that we are going to use here, like the idea that we can be infinitesimally close to something or actually there, right? And in usual mathematics, in continuum mathematics, that is captured by notions of limit and continuity and all that stuff. In our case, it is a much more pedestrian and much more sort of low-tech version of that, which is, you know, you are either there or nearly there, and that's it. There's no more granularity to it. You can be almost there or there, right? And that's basically so that idea of almost there is what edge places give us. So with that notion, the concept of a vector then becomes very straightforward, right? So a vector in usual geometry can be understood in many different ways, but in a fundamental sense, you know, going back to the etymological use of the word vector, a vector is something that is defined from a position and a trajectory that is projected, right? So even if you want to think about the technical definition of tangent vectors in manifolds, all the way back to Euclidean geometry and oriented segments and things like that, at the end of the day, what you have is a base point and a declared direction, right? Which is saying, hey, I am pointing towards that position, but I'm not there, right? That's what a vector captures, right? It's saying I am moving in that direction, but I'm not there. So in our context, that can be captured very easily with edge places, right? So if you say are in this vertex here, and you say I want to move to this other vertex there, but not get there, so I'm not actually traversing the edge to get there, then what you can say is just simply point to the edge that will take you there if you were to traverse it, right? So the actual vector at that point is a directed edge from the vertex place to the edge place in that context. So in this particular case, I am computing. So let me do it for this thing, right? So this thing is showing the one-dimensional vectors at every point, right? One-dimensional means that they are defined by this sort of procedure. It's like you are at a place and you declare what direction you want to point at. So of course, the number of vectors is going to be the number of edge places that are incident to your vertex. So you know, if I move it around, you will see that in different nodes you get different vectors, always pointing to the edge places that are incident there. Okay, but this notion can be extended, right? If there are two things that you can reach from your position, right? I mean, okay, let me argue for this in this way. Imagine that you live in a one-dimensional world, right? If you live in a one-dimensional world, there's really only two vectors that you could ever define in this sense, right? Because if you see a point that is not where you are and you want to point at it, you can only do two things. You can either point forward or point backwards, right? So in a one-dimensional space, in a one-dimensional universe, the story of vectors or the story of multivectors will end in that very, very boring fashion. It's like, okay, you can either move forwards or backwards, that's it. But the moment that you have something in 2 dimensions, which allows you to say, hey, I have these two independent directions that I can walk into, and they will bring me to different locations that are not collinear, they are independent in some sense. So the way that we can capture that from the location you are is to say, hey, I can point at that location, and I can also point afterwards at that other location. And in this process, I pointed to 2 different locations, right? But it's important that we keep some kind of track of what order of enumeration we follow, right? Because it's basically saying, hey, first go to that location, then that location. Yeah, that's well defined because I find them, right? So that way you have an actual list of locations that you could visit in principle from your position. And so that's how you define bivectors in usual geometry. So for that, I choose dimension 2, and maybe I move it to somewhere where it's a bit smaller. Let's see. Yeah, maybe there it's quite clear. So you can see that a bivector is essentially just a triangle in that position. So that little triangle is actually an oriented triangle because it always has the base node, the vertex place as the first element, so to speak, and then essentially captures the order of other edge places around it. So that's why you actually get many. You can see the picture that there's well, in this case there's two, right? Because you have first this edge, then that edge, or the other way around, right? If we go to a different vertex here, there's more, right? Like there's all these possible combinations. So that's multivectors, right? That's the notion of multivectors. And the reason I'm bringing up multivectors when talking about shapes is that you can, if you imagine this idea of living in a one-dimensional universe and then a two-dimensional universe, and so sort of thinking proactively what kind of geometric definitions you can make in those universes, you realize that you can only ever define a bivector if you live in a at least two-dimensional universe, right? If you're in lower dimensions than two, you would never be able to define a bivector, right? Or if you try to, you get like some trivial answer like zero vector or something, right? So so that's why, you know, having these objects well defined in the infrageometric sense, it's important to talk about shapes. So having at a given node, having multivectors up to a certain dimension is important to define what are the maximum shapes that in principle could be incident on that position. And let me make this much more concrete. Okay, so go back to the triangle example, right? We say that intuitively, yes, this looks like it has the simpliciality condition, so this might be representing a shape. But actually, if we were to represent the bivectors that that emerge from this, or at least the vectors, right? We will get this sort of multi-vector visualization thing where, you know, if we're looking at the vectors, we just, you know, these are the vectors in each one. If we're looking at the bivectors, because there's three, now there's basically all these surfaces that you could in principle draw between them. And because we have three, we also have the higher arity edges here that are like full volumes, right? And here the important bit is that this shows that maybe the right notion of shape doesn't coincide intuitively with the notion of chunk of space. And that's basically my whole point in today's stream. I don't want to make it very long. I just want to really emphasize this point and chat, and you guys can basically attack my position and see how this looks. So
Well, so are you saying that there's a volume element in this triangle?
yes. So let me elaborate. Let me elaborate a little, because this begs a bit more clarification. So intuitively speaking, right? If we were thinking about just simplicial geometry and have the simplicial complex model in our heads, we would want to say that if this is to represent a triangle, right? And this is to represent like an actual geometric triangle, then we should be finding something like this, right? We should be finding a set of multivectors, or in this case, bivectors, that interlock with each other in a simplicial way, right? And I think I did it correctly. If you can see, oh no, actually I did not do it correctly. This one here is both going in the same direction, but I think all others are going in opposite directions. And you know, you want to make sure that when these things interlock, then there is the notion that those things integrate to a surface. And what is the analogy here? The analogy is, if you have a collection of tangent vectors, right, that remember these are oriented edges between edge places and vertex places, right? So if you have say something like, maybe I don't have it drawn here, but if I draw very quickly, so if you had, say, edge place, sorry, vertex place, and then some edge place here in the middle, right? And then you had a tangent vector edge that looks like that, and the tangent vector edge that looks like that, right? This represents a infrageometric version of there exists a shape, a one-dimensional shape between, like there is an actual shape between these two, right? I mean, it looks very naive, because in this case, it's just like, oh yeah, two arrows composed to a longer arrow. It looks very naive. But when you try to make this into a general principle for arbitrary dimension, then it becomes highly non-trivial how to do, right? Because the next example, this is the example of a one-dimensional shape. The example of a two-dimensional shape is already this kind of picture, right? It's the minimal three-dimensional, so it's the minimal triangular combination of edges that you can make, because you need 3 nodes and you need a simplicial collection of edges on them. So you need all the sort of lower arity ones. If you have those, if you want something that looks like a simplicial complex just on the nose, that's the simplest thing that you can draw. So that's, how many? 6, right? It's 6 different edges that you have to account for as what would be a simplex, right? In usual discrete geometry. Same here, like a one simplex here will correspond to 2 infravectors. A 2 simplex here will correspond to 6 infravectors.
All right, hold on. I have a question. So, like in this example with the one simplex, this edge that you drew on the screen. So we have an edge connecting these 2 things, and you have tangent vectors at the left point. You have one outgoing tangent vector, let's say, that starts at the point and travels with some velocity into the edge, originating from that point, and then that's indicated by the yellow arrow at the left.
Yeah.
Right, and then the arrow going from the interior of the edge to the right point is, I want to say that's kind of like a tangent vector in this tangent space of the right point.
Yes, that's correct.
Okay. And then so like a left facing, like the opposite of the tangent vector at the left point would be the one going from the interior of the edge towards the left point. So you have like these 2 tangent vectors, and if you want to scale, if you want to talk about velocity, you can scale them. You kind of have like a vector space, tangent space at point A.
Yeah.
Okay.
So I'm highlighting this graph because that's exactly right. So orientation of, so the tangent space at a point is defined as the collection of directed edges that you can build with that node and all the edge nodes around it, right? So no specification on where the node plays the role in the directed edge, right? So there can be, incoming and outgoing arrows, right? So similarly for multivectors, right? Like they can be, oriented in any possible way, mostly because, in the case of the edge graph, which is this graph, right? Like the graph that you build out of just the edge places. So essentially the line hypergraph, for those of you familiar with the term line hypergraph, it just replace an edge for like all the lines of incidence of that edge. In this graph, paths are actual sequences of tangent vectors, right? Because you would always go from here to somewhere else, and you would be concatenating tangent vectors in this sense. And that's what gives us the idea of integration, right? Like you have a set of infinitesimal displacements or tangent vectors that then integrate to a whole path, right? So if you give me some random collection of tangent vectors, they will not, in general, integrate to a whole path, right? And so that's why we have this kind of example here, right? Like where you have your fully labeled edge graph, and then you consider an actual path here, right? Like this is the path, the concrete path. And so if you think of that as a collection of directed edges, there's a very concrete arrangement that actually integrates to what I call a curve in the graph, right? So a curve is now made of just a sequence of nodes or vertex places that that have oriented edges as elements, right? So a curve is like piecewise one simplex, right? And so you can only build it by concatenating the right orientations of pairs of pieces of infra arrows, right? Of infra vectors here. So and then I also, just for the record, I also include this notion of displacement. So we become a bit more sort of detailed in our terminology. There's a path, which is in general any actual path in the edge graph, right? Then there is a curve, which is a particular set of paths that actually corresponds to having edges in our fully integrated edge transitions, right? So basically, when you go from node to node via a single edge, right, in your hypergraph, and then we have what I call displacements, which are sort of net paths, right? Like when you go in this example, is clear, right? Like you have the actual path, which is the collection of directed edges. You have the curve, which is the whole edges being traversed, and then you have the displacement, which is, for example, here I have a displacement from 1 to 2. There's no curve from 1 to 2 because there's empty space between.
Right.
But you can nonetheless measure that you went from 1 to 2, completing your hypergraph, right? So that's still a notion that we can deal with and compute with, and we call it a displacement, right? And similarly, the whole thing from 1 to 13, just the beginning to end of the path, that's also a displacement. And the reason I'm giving these names is because they are all made of the same stuff. They're all directed graphs on your initial edge graph, right? So they are equally computable. They are amenable to all the processes, the rewriting, all the stuff that we are in principle intending to do to these things, right? So the whole story becomes a little bit more complicated when you try to do higher dimensional stuff, right? Like this to me seems very intuitive. Sure, you have an edge, you put a line in between, this happens. But this picture might be a bit deceiving because this kind of situation, right, might very well be this kind of situation, right? Where if I draw this again, I draw on top of the picture, this kind of situation might be happening in this way. Like I start here, this is my position 1, and then I travel to the middle, and then I travel to here, which is my position 2, right? So in this way, you can say, if I take these tangent vectors, which I guess I can represent in here, by the way.
Well, it's a tricky thing. Like in the simplicial complex case, you would say we have a triangle and all of its edge components are there, and so are its vertices. So defining a triangle automatically includes that. So when you say, oh, I want to go from this corner to that corner, you have implicitly the volume or the area of all the points in between, and you also have implicitly the edge component that will take you there directly.
Yeah, exactly.
Right. So this, if we're deviating with hypergraph structures away from full simplicial complexes, that is, we can include like the area of a triangle without including necessarily every component of its boundary, then yeah, you would have to cut through however much area is allotted in the interior, to cut through the interior of the triangle to get to the other corner of what would be the straight edge,
right,
1 to 2.
So exactly, and so the main point here is that from the point of view of walking on your spatial hypergraph, there's no real distinction between a ternary edge place or a binary edge place or, you know, arity 100 edge place.
Mhm.
Because from the point of view of the, you know, the little spaceship traversing the space, you know, they're going to see the same thing. They're going to see, okay, I was once at a node, then I went through some space, and then I arrived at a node. Right?
Mhm.
So their perspective is indistinguishable, right? So, and I think that's okay, because, you know, I don't think we should believe hyper edges represent space directly, right? I think that's exactly, I think that's the one point I'm trying to argue into this live stream, is like to drop the more visual, direct, intuitive picture of infrageometry in favor of something that is technically equivalent, but allows for like a bit more serious definitions and a bit more articulated formalism. And that is to say, you know, if you want to really think of nodes as bits of space, if you insist on it, which might be a bad idea, I don't know. But if we are on this premise that this is a good idea, that nodes are like little bits of space, then there's no real analog of what the edges are in conventional geometry, right? Like, because in conventional geometry, everything is points, right? You don't have any, like, when you have a topological space or a differentiable manifold, you don't make distinctions between points, right? You don't say, hey, there's some points of this kind, some points of that kind. Like maybe some of the non-standard analyses, you know, with infinitesimals and something like that, maybe they are doing something similar, and at some point it will be interesting to see if there's some analogy that we can build there. But I want to emphasize that conventional geometry doesn't have a analog for what our edges represent, right? So the fact that, sure, we draw a little triangle between three nodes kind of looks like a surface, and it's like, oh yeah, that's happy, you know, like,
I mean, I
we
would
have a
say open sets. You know, the open interior of a triangle is represented by a three arity edge, or
right.
that's kind of what makes sense to me. And you know, you could exclude the you know, not include the boundaries and just have the interior open on its sides, and but still include the vertices.
But that's kind of weird, right? Because
Yeah,
what is
yeah, it's weird.
is an edge without its nodes, right?
Um, you mean a triangle without its sides, or I mean, you can have the open
I mean,
interior of a
it's well,
triangle union the three vertices as points.
yeah. No, I understand. From my mathematical point of view, I have no issue. But from a computational point of view, where these things are the discrete data structures, like an edge is exactly the collection of the nodes, at least at this level of undirected sort of hypergraphs, right? So it doesn't really make a lot of sense to say, hey, I can consider the abstract edge without the nodes. I mean, I could think of it as some kind of pattern matching, that I'm just saying, hey, there could be any three nodes that could match here, but that would be a strange notion of an open set, right? Like, to me, an open set will be exactly like an open neighborhood, right? Like, where you say, hey, around this point, there's like some non-definite places that you can extend to without, you know, knowing where you're getting to, which is the idea of an open set, right? It has like a fuzzy boundary, like it's not like well delimited. That, to me, that's what a neighborhood would be, in my opinion, like this kind of picture, right? Where each blue node, which is a vertex node, a vertex place, has this little sort of like set of places that it can be near to, right? So that, to me, would be the analog of an open.
Yeah,
open
yeah, I
set.
get that. It's like, you know, infinitesimally, what point, how much space of the object is available to you
Yes,
to travel
exactly.
towards.
Exactly. Yeah. And that's why, so what I'm trying, my bottom line is, I think we need to drop. I mean, it's not that we ever took this intuition seriously, or we actually made definitions that were explicitly using this definition.
Mhm.
But I'm maybe only speaking for myself here when I say I have to drop the intuition that the edges are like little chunks of space. Put it in other terms, we have to drop that edges are like little shapes, basically, right? Because, I mean, if we are to take seriously this approach, I think that's basically what this is suggesting. And so we have the infrastructure to do the hypergraph generation stuff, to like generate like models, like in the Wolfram Physics project, and we have the ability to process all these hypergraphs with all the algorithms that we have. But if we want to talk about something like shapes emerging from this sort of infrageometry framework, we need to start thinking about these kinds of things, right? Where how do you patchwork shapes out of this infra stuff, right?
So I mean, yeah, I mean, in my mind, if in the simplicial complex case, you know, you have 2 points and you make an edge connecting them, then you have available to you the ability to travel to those interstitial places along the edge as places that you can say that this is my position now. I'm a point and I'm moving around this object. So in the sort of ontology of, okay, well, let's think about what if space is discretized and the available locations that you can go to are limited, and the connectivity of, you know, what point you can go to from a given point is limited and defined by like the graph or a hypergraph. Then it's like you're talking about having the locations are discrete, so you can't go in between. You can just go towards. You can arrive at these different locations at the vertices. I'm just thinking out loud here.
I mean, I don't know. I need to understand. I mean, I would love to hear what Nick or James have to say about this thing. Like, it seems that the natural definition of multivector here, you know, in this little example, if I go to 2, it seems that, you know, or 3 even, like that looks like a volume element, like a little volume chunk in a hypergraph that intuitively so far we would have thought as a surface analog. But like it's like the edge place idea pushes you in this direction because it naturally leads you to the definition that your edge places that are incident on a node are like the infinitesimal points, and so you make all your tangent vector definitions based on those, and then this multi-vector definition becomes natural. But when you go all the way back to this kind of perspective, you realize that, hey, I have multi-vectors of dimension higher than what it looks like my local dimension is from the naive interpretation of the hypergraph. What do you think about this?
Can you switch between the 1, 2, and 3 again?
Say it again.
Oh, okay.
Can you just?
Oh yeah. So what this is doing is basically just each. So one is you take the base node and one edge place. The 2 is the base node and 2 edge places, right? So these are triangles, right? Like that triangle, that triangle, that triangle. And 3 takes all 3, but also all the orientation. So there's like only one there really, up to orientation. Like if I did neighborhood, this might be clearer. Yeah. Oh, but I don't have an option for this. Oh yeah, because the neighborhood is maximum dimension. Yeah. So yeah. Anyway, Nick, do you have any thoughts?
Well, I'm kind of thinking, like in geometric algebra, you have I think there's a way to define a manifold. Like at each point of the manifold, you have a pseudoscalar, and that's defines the geometric algebra at this point, right? So it's kind of very analogous here. Essentially, you have, but it's like some partial definition of your local geometric algebra because the different connectivity, you have a different connectivity at each vertex, right? So essentially you have a bunch of edge places that is available from that vertex, which defines the dimensionality of your geometric algebra at this particular point.
Yeah.
So it's not like uniform across the whole hypergraph. It's like at each point you have some different connectivities, which defines a different pseudoscalar, which can be, which is essentially just a product of all the possible vectors, all the possible edge places that you can reach from that particular vertex, right? And essentially you can,
Yes.
that defines the whole structure.
Yeah.
Yeah.
Yeah. No,
Just
exactly. And yeah, go on.
It's like not clear to me. It's like different kinds of geometric algebra properties, like algebraic properties, where those come in. For example, like why the vectors have to be anti-commutative. What even, right? It's the orientation, right? So it's because you have some intrinsic orientation of those vectors, but those have to be from the vertex to the edge place, because if you multiply them in different order, the orientation should be different.
Yeah. Yeah, and I think that like that pseudoscalar that you're referring to is basically like captured up to orientation, up to ordering. It's basically this neighborhood thing, right? Like at every vertex, there's like one thing that basically takes up all the edge places around the vertex. So, but okay, so if you take that intuition, let's say, imagine what I find a bit confusing to think about right now is that, you know, conventional, let's think about conventional space, right? Like our ordinary space, like three-dimensional Euclidean space or something. Like it has the property that whatever point you choose, if you did this construction, you always get the same result, right? Like you always get like three independent directions, and however the order you choose or whatever, it doesn't matter, but you always get the same space. So the way you can think of it is that if you scatter some sample points in your space and you were to like construct the discrete looking multivectors that come out of those, what you would see is that in every point you would have the same size of the pseudoscalar or the multivector, which is to say, in very simple hypergraph terms, that if you were to have a hypergraph analog of that space, you would need a homogeneous degree hypergraph, right? Where every node has the same number of incident edges, regardless of arity. You see my point?
Yeah.
Talking about you would populate the volume with vertices and have connectivity resemble like a three-dimensional kind of thing.
No. So that's
Every
exactly what I'm
point.
trying to say, that you don't need to. Like you can do it that way, but you don't need to do it that way, because if your only probe for the fact that your space is three-dimensional is that you like, I mean, there are many ways in which we can probe that the space is three-dimensional. Let's take the infinitesimal approach to three dimensions, right? Or to dimensionality, which is like, you know, I'm here, I see my hand going in one direction, then I can go in another direction, then I can go in another direction, right? Like I can do this with my fingers, right?
Mhm.
That's my little like measuring probe that I am in 3D. Like I do this, and then, you know, maybe I go somewhere and it's completely flat and it's like no longer can do that or whatever, right?
Yeah.
So if that's my probe to dimensionality, then the analog of that in this infrageometry story that we're building up here is basically just taking the neighborhood and just counting the number of edge places, because that's going to define the dimension of the largest multivector that you can build, or what Nick referred to as the pseudoscalar, which is the same thing, right? So that then gives us this notion that dimension as degree in usual sort of hypergraphic terminology, a degree means the number of edges incident on a node, on a vertex, right? But crucially, if you were to believe the story, like edge have their edge places, and that's what defines the multivectors and blah blah blah. If you believe this story, like the story that I tried to build up a little bit with this, right? Then local infinitesimal dimension just corresponds to hypergraph degree. So, something that could in principle resemble like a three-dimensional space, which is where all nodes have degree 3, right? So that your local pseudoscalars will be of size 3. That can have very complicated, like actual.
Well, so like like a square grid, each vertex is connected to 4 others. It doesn't make it 4-dimensional. And a hex grid is 3, or a triangular
that's what I'm
grid.
saying. So that's what I'm saying. Like a square grid, in this sense, will be a model for 4-dimensional space.
I'm not a fan of that idea. Wait,
Yeah,
4-dimensional.
Exactly. So
there has to be a notion of like, you're going to the right, going to the left are opposites of the same one dimension.
No, but you have that on each dimension, right? Already. Like going back and forth the same dimension, you have on each node of the square grid. Help me out, Nick, with can I do a square grid?
Grid graph.
Grid graph.
You have like a list, like 5 by 5. No, 5 by 5. It's an actual
Okay.
size.
So in this situation, right?
Yeah.
The edge place is actually. Let me see if this works. No, Nick, you know a quick way to turn this into a hypergraph?
It already is
Yeah.
technically, but
Just extract the edge list and wrap it with the hypergraph.
Yeah, well, I don't think that works.
well,
actually.
you can add 4 arity edges for the squares. Let's say.
I don't think it works. Let's see. This can be a.
Well, maybe also replace those undirected edges with list. So first do that, yes, edge list.
Yeah.
Then, well, evaluate it because we can
Yeah.
see there's like a directed edges, and then like a list triple add at that thing.
Okay. I didn't know that. Yeah.
Yeah.
Okay. And then sure. Okay, I was missing that actually in one of my other functions. Sure. Interesting. So do you know if I can do?
Yeah,
What is
you can try vertex coordinates like a graph embedding of the above, the grid graph.
Graph.
Or maybe just try graph layout and grid embedding or something. Maybe would work.
What? Say it again. Graph what?
Graph layout.
Layout. Yeah, layout.
Yeah, there's a grid layout, I think, already.
Yeah, but it's probably not going to do it because of the edge thing, the weird.
Well, I'm not sure about that. We can try. Grid.
Agreed.
Grid embedding. Yes.
Okay, yeah, it did work. Nice. So what I can do is do the grid, right?
Yeah.
And now what I can do is neighborhoods graph of grid. So my point, so this is cool. I'm actually at the point where I can live code and show you some and answer some questions with the actual things. So my point, Dugan, is that
Wait a minute. Question.
Yeah.
This is a functional design question. When you have edge places grid, does that hold first and then like replace grid with one that has updated grid edge places?
Yeah.
Or should you say grid equals edge places grid?
No, it's not mutable if you're asking about that. It just returns a new grid.
Uh-huh.
Yeah.
Okay.
Yeah. So my point is, we have this graph that, because we humans, I mean, it's kind of neat that I got this thing without the grid embedded, right? Because if you look at this graph, I personally don't immediately think about a grid, right? Like the grid geometry, but actually turns out that yes, it can be put into grid geometry. So this is speaking to your brain, yeah, that should definitely be two-dimensional, right? But my point is that if you buy into this narrative of infrageometry that I've built so far about edge places, how this infinitesimal story and so on, when you go and compute the neighborhoods, sorry, this bugs me so much. When you go and compute the neighborhoods, what you get is this, right? Which is 4 RE, so quaternary edge everywhere. So this is a 4-dimensional space, right? This is the connectivity of a 4-dimensional. This is the
Except the boundary where they're free. And
sure,
the
yeah. Boundary points non-standing. Like the bulk of this is exactly what you would get in the bulk of a 4-dimensional space if you were to scatter a discrete number of points and do this dimensionality probing by local independent direction counting, right? So,
Right.
so my point is, yeah, this is a good example. Actually, I'm gonna keep it here in the notebook. This is a good example to like really drive home this counterintuitive point. But beyond this is that you could have this situation, right? This happened to be also a regular graph, right? Not only regular degree, but also regular in the sense that there's only pairwise edges and they all have the same incident numbers. You could have this situation where the arity of your nodes is whatever, right? Sorry, the arity of your edges is whatever. So, there's ternary, quaternary, there's all manner of incident edges that contribute exactly in a way that only 4 are incident at every node, right? So that's sort of further breaking down the intuition that edges should capture some sense of space, right? Because I mean, to be honest, and to push back even in that, the square grid should somehow be two-dimensional in some sense. Like realistically speaking, this seems that every time that you're at a vertex, it seems that all you can do is like travel to a one-dimensional object, right? Even in the naive picture where the edges are the dimensions, right? Like even in that picture, this looks like a one-dimensional, like piecewise one-dimensional space, right?
Yeah, I mean this connectivity is, you have like walking around New York, you can only walk along the streets.
Yeah.
You can't walk through, you can't cut a corner from one intersection to the next intersection through a building. You can't walk through that.
Yeah.
Whereas
Exactly.
in an open field, you can walk in any direction you want. So if you're trying to say, oh well, you can cut a corner so long as there's an edge defined there, like a path that's cut through, or you have a higher arity edge. Like, I mean here, like if you added the squares as hyper edges, what would that give you?
I mean, you mean the squares and the triangles?
Let's just start with the squares.
Well, the
Like,
squares would add.
would that allow you to travel along the corners?
It would, yes.
Mm-hmm.
So with this interpretation, then you will have 4 squares per vertex again.
Mm-hmm.
So it would make it 8-dimensional.
Yeah, in that definition.
Yeah.
I guess the
But-
you know the dimensionality reduction would come through having some sort of notion of linear independence or dependence of available tangent vectors at a point.
Yeah, exactly. And that's why I was considering something like this, right? Like this kind of situation. Like if you are able to construct, like imagine that you only give me this information, right? Like this looks like it came from whatever kind of hypergraph. Like I don't know. But if you give me sort of like this multi-vector directed hyper edges in this specific arrangement, then I know for sure that there has to be this structure in the background. Like this cannot happen in any other way, right? So there's several threads here to pull from. Like there's this idea of, it seems very intuitive how to integrate paths into curves, into displacements, this kind of idea. Like this seems like a very simple story, right? Like it's very clean. Like, you consider all the possible directed edges from vertex places to edge places, then some concatenations of them build up to actual paths in the whole thing, so you call them curves. And then only then you say, yeah, I integrated this infrageometric information integrated to some whole information, whole geometric information. That story that seems so transparent there, it's not so clear to me in the multi-vector case, right? Which is, but it should be, right? Because that's what usual manifold integration is about, right? Like you have a when people talk about integrating surfaces, what you have is a bivector field, right? That what defines at every point is a tangent plane to that surface. And so you basically, like in the same way that you can think of an integral curve of a vector field as something that is being swept by the flow of the vector field, the surface is sort of like sweeping in one extra dimension, right? And it's sort of sweeping an entire sheet of points, right? So that notion of integration is very prominent in geometry. Is basically, it applies to all dimensions, but the one that we visualize the best is the one-dimensional one, because it's the one that corresponds to sort of like journeys in space and like displacements.
Yeah. The total tangent manifold to a manifold has double the dimension as its own separate abstract manifold.
Yeah, sure. Yeah,
Which
because
is kind of what you're talking about, it having been swept out, like a path on the plane, and then if you look at the path along with all of its tangent spaces at every point, then yeah, you have a.
I mean, I'm referring to something that is a bit more concrete in the sense that, so I'm not referring to the fact that your tangent bundle has as a manifold double the dimension, because that's kind of a trivial thing.
Right.
Just putting together base space and fiber space, and it's like, sure, they happen to be the same dimension, so it's double the dimension. There's nothing really profound there. What I'm saying is that I'm phrasing the problematic in infrageometry, in the infrageometry project, in this following way. We have a quite strong sense of how curves are integrated from directed edges, right? There's a very direct way to do this, right? Very unique and very clean. Once you define your tangent vectors, or the discrete analog of tangent vectors as these directed edges here, it is clear that concrete arrangements of such directed edges, quote unquote, integrate to whole paths in your edge graph. And those in turn also integrate to whole displacements in your graph as a whole, right? So that seems to be very clear. And from very early on in the project, this was like, okay, yeah, this is a strong intuition. Now, we should be able to, if we are to claim that we are capturing geometry in general and not just like paths, then we should have an analog to surface integration, right? And surface integration is something that's entirely in continuous geometry, right? It's entirely analogous to curve integration, but I don't know how people think about these things, because I've worked with them so much that to me is like second nature. But you have normally, when you think of a vector field, you have a field of directions, right? That's what a vector field is a field of directions. So you can imagine like in a little diagram that you have like little segments, little, bits of segments in every point of a space. Like you probe a point, there's like little segment, probe a point, little segment, probe a point, little segment. And so integrating the vector field basically amounts to taking a pencil and sort of trying to trace the segments along the line, right? So imagine just one dimension higher, everything bump the dimension by one in that picture in your head, right? Like you, instead of having a sheet of paper where you will draw, you have a three-dimensional space, and instead of having little segments in space at every point, you have little planes, little in space, right? So it's the same idea, like you have this field of tiles, and you need to sort of like you have to sweep a sheet that happens to lay tangentially to all these tiles, right? Like maybe it's a kind of VR game, like you're doing that, right? Like you can imagine doing like drawing in 3D. So my point is that we need to be able to do that, like in a completely transparent, clear, uniquely well-defined way, in the same way that we do it for curves here. Like this seems very transparently analogous to the curve integration case by infinitesimal vectors. And what I was trying to do here is to do the same thing for bivectors. I mean, and higher, but I think if we manage to do it for bivectors, it should be pretty obvious how to go higher. And that's why I landed into this kind of semi-paradox or like uncomfortable thing where it's like, yeah, what looked like this triangle looked like an element of space, like a simplicial bit of hypergraph that should be encoding something like a surface, but there's three-dimensional multivectors there. So it's like, this thing is like these multivectors here that are three-dimensional are like too thick. Like they are extending to a third dimension that doesn't exist in this plane, right? Of course, there's nothing of that because this is all combinatorial. There's no dimension. This is all analogous. But in terms of how we are going to define the things, it's a bit confusing.
Wait, sorry, can you just repeat what's the issue with to me?
Yeah. So the issue is that if you take the edge place approach to the infrageometry project that we've been doing so far, the notion of tangent vector is very naturally defined. The notion of tangent vectors integrating infinitesimally a whole integral curve is very well defined. But the most natural notion of multivector, which is that of take the number of points that you can reach and then join them, that already breaks this notion. Okay, I just had an idea, and maybe we can close with this idea. How about we define bivectors in particular? What do I want to say?
Well, is your overall goal is to define a multivector just around a vertex in arbitrary hypergraph?
Yeah.
Right.
Right.
Well,
yeah.
yes.
So
Yes,
yeah.
That's the goal. That's the goal. Yes, but informed by the fact that this is meant to be analogous to geometry. Yeah. Right. So let me tell.
But does it have to be like globally aware of the whole hypergraph, or it's purely local?
No, it should be purely local. Should be purely aware, only aware of the incident structure of that node.
Okay.
Right. So I just had an idea. So how about, so right now this is the blind definition of multivectors, right? This takes literally all adjacent nodes, right? All adjacent edge places around the node. So how about?
Well, yeah, I mean, and I have something to say about this because
yeah,
I don't want to like hold your thought.
Yeah, no. Let me phrase the idea because we might be thinking of the same thing at the same time. And I don't want to forget. So how about we require simplicity as a condition for a multivector to exist? Meaning,
like saying that you have the boundary components.
Yeah. So meaning that if I were to take this hypergraph instead, right? If I were to have this, I mean, right? This thing is not a simplicial.
No.
This is not a simplicial shape, right? Because it doesn't have, it's not filled in by a ternary edge. So because these two edges are not the boundaries of something that could be filled in, right? Which at the end of the day is a check that is local, because it's just checking for the existence of a, you know, n+1 dimensional shape
Mhm.
right there. Then I'm not going to draw bivector between them, because although there's two different directions, these are sort of combinatorial directions. There are not geometric directions, because I cannot sweep my arm between
Right.
them. Because that's what a bivector is. A bivector is not the fact that you have two independent directions. It's the fact that you have two independent directions, and you can sweep your arm between them, and there's continuous space between those two independent directions.
Right. Right.
So that to me makes more sense, right? It makes sense that this has no bivectors. This has bivectors.
Yes. Yes. And if you
Wait, what's
scroll
the
up,
difference?
the difference is that this one has the area that's defined by that 3 area
Oh. Yeah.
triangle, and
Yeah.
so you can continuously sweep along from
Yeah.
from one corner from one edge to the next at a corner, and have a 2-dimensional element defined in that sort of tangent space. And
So
just having, so if you scroll up some,
yeah.
some more, I think it's like towards the top, you had this thing. What? Down. Sorry. A little bit more. There was a manipulate where you had you're going through the different neighborhoods of that plot.
Oh,
Here.
this?
There. Right. So here you have like a arity 3 or 4 at that point. Like, okay, so just because you have like a triangle and at the corner you have like this other edge going off of that. So like you have a union of these two different dimensions of spaces at that point. So you have like a 2-dimensional element going into that triangle, but then you have a 1-dimensional element going to the left, and you can't connect them to make a 3-dimensional element. I think we're having the same thought.
Yeah, probably we are. What do you think, Nick?
Oh, hold on, I was spaced out. I wasn't paying attention to that.
We're
Last
saying because this has a.
So let me make the argument very clear, and then maybe we can close the stream.
Sure.
It's getting late here as well. So the argument is as follows. Previously, and I wanted to explain with these two diagrams, right? Like previously, if you compute the multivectors of this spatial graph, which is the triangle, you get 1 vectors and 2 vectors, right? Like that's the 1 vectors there, and that's the 2 vectors, right? Because the 2 vectors are just combinatorially taking all the possible arrangements, right? There's nothing. It's not checking for any local structure, just literally just taking the list of edge places and just taking all the possible orderings. So what we are saying is that maybe these bivectors are just not defined, because you can know that this is an edge place of arity 2, and this is an edge place of arity 2, and then there is no edge place of arity 3, in this case 2 + 1, that is also incident in the same place, right?
Right.
So in this case, you will be able to draw this kind of thing, right? Where you can sweep an area between the binary and the ternary and the binary, and the binary and the binary, because these things are sort of fully transitive. Right? Like if you can sweep an area between this place and this middle place, and then this middle place and that other place, then you can swipe the area between the two extreme places, right? So
So what again the arity represents? It's like the fact that there are different arity of available edges to the vertex.
I mean, this is kind of like recovering this idea that arity has something to do with dimension, right?
There's an inseparable relationship between the two nodes, the two other nodes that you could be pointing to in the ternary edge. Previously, they were separated relationships, but because that ternary edge exists, it's like there's a space
Yeah.
between them. There's an area
Yeah.
between those other nodes.
And the way to think about this, by the way, is that, even though, I mean, our computations are local, but local here means local in the sense of a hypergraph. So you're actually taking the whole edge structure. You're not blind. Although the objects themselves are defined on the edge places and they look sort of infinitesimal, but your objects are primitively just whole edges, right? So they are primitively, this element and that element for this edge, binary edge, this element, that element, and that element for the ternary edge. So you can know that this edge is simplicity related to this one because it's a sub edge, right? It's a subset of the edges. And of course, we might want to be a bit more sophisticated than just subset, but that's kind of the basic idea, that you check some kind of simpliciality and you define, maybe it's wrong to say that we have to define multivectors like exactly this way, like between the edge places, but we might want to define them. I mean, I think multivectors will have to be defined between edge places. I think there's no escaping that because there's nothing else that we can build them on because there's no more infrastructure there. But how we build them exactly, like which are the multi vectors, like given a structure of edges in a place, that might be, a bit more subtle. We might want to say something like, connecting edge places of
Okay, can you say it's like maybe arity relates to a completely different signature of your geometric algebra? Like if you're just sweeping a vector that is like connected to the binary edge, like to the edge which is the binary edge, you're sweeping, that's the usual bivector. You're just multiplying those vectors together. But when you multiply two vectors of different arities, it's like I don't know, the vector from, essentially what I'm saying, that the vector from vertex to the edge place which is binary, and the vector from the vertex to the edge which is ternary, is like a completely different kind of vectors, though maybe they just belong to a different geometric algebra. And when you multiply them together so that they sweep them to essentially from one to another, making bivectors, maybe you're just not allowed to do it, or maybe it's just something in between those two geometric algebras altogether.
Yes. That might be the right approach as well, actually.
Infrageometric algebra.
Yeah.
Unless it's like a fractional one, it's like if you have a three-dimensional geometric algebra, two-dimensional one, what is the like free 1.5 geometric algebra? Essentially, you're connecting vectors from one to another and sweeping from binary edge to a ternary edge, right? That's kind of structures they're in between somehow.
That's true. But it's still a little bit like this notion of a wedge product. That, I mean, that's another question, actually. Like, one thing is to have a bivector being primitively defined, right? Which is like an oriented surface, infinitesimal oriented surface, right? That's something that is well defined. You don't need to define it by the wedge of two infinitesimal vectors, right? And another thing is to say, well, if you give me a vector and then a vector, can I construct a wedge of the two that is this thing? But it is weird because, you know, if I'm multiplying something that you understand as a two-dimensional bivector, like the most naive interpretation of what you said is that edge places of binary edges correspond to vectors, edge places of ternary edges correspond to bivectors, and so on, right?
Yeah.
So under that interpretation, the wedge product of those is not really a fractional thing, because if it were
Well,
to
by
work,
itself it's not, but the part of, but it's a part of geometric algebra. I don't know, of a different kind of geometric algebra of a different signature, because you're kind of mixing those whole integer geometric algebra, dimensional geometric algebras together. It's like, you know, it's like you take a space-time algebra and mix it with a conformal one, or whatever. You know, it's just weird here.
wait, no, but usual geometric algebra already mixes dimensions, right? Like,
No,
you-
I mean, it depends how you define dimension, but there is just a number of vectors, right?
well, I mean, you can have multi-vectors that are not the product of vectors, right?
Or if you, because
That's-
there's a sum. What do you mean? Do you sum them over usually? It's like multi-vectors is some scalar plus a vector plus a bivectors.
I mean pure bivectors, for example. Like you
Those
can
would be
have,
No, bivector. Usually just some product, geometric products of vectors.
no, but I mean, but you can have something like it's like the linear combination of some basis vectors, and therefore, like, not all bivectors are factorizable as two vectors being multiplied, right? Maybe a linear combination of bivectors or of one vectors, right?
Yeah.
So anyway, my point is that there is an issue here that we need to resolve. Like we need to think about like carefully, which in some sense is like the essence of infrageometry, right? It's like, what the hell does it mean for a hypergraph to represent space? Like, we are going around this problem over and over again, and it's kind of fun to like develop a bunch of stuff and visualize a bunch of things and then come back and realize, wait, what does it actually mean for a hypergraph to represent space? Because we're still not fully clear on that point. So, but I like the idea to think of, I mean, for me, it's like the edge structure around the vertex place gives you the local connectivity, so it gives you information about space there. So if we take the notion of betweenness, then the notion of simpliciality is induced, right? Like you say, you know, these are 1, 2, 3. Oops, yeah, I think something overrides it. But anyway, so if we have 1, 2, 3 edges here, like having an edge that says 1, 2, and 3 all together, and then having another edge that says 1 and 2, we should be able to exploit that information, right? Like, before, we were just not even paying attention to that information when computing things at a given vertex, right? But if those lists of nodes are representing betweenness information, then the sort of nesting of those things, which corresponds to the simpliciality of the structure, should be used in a crucial way to define whatever local geometry, right? And computing these multivectors, to me, is exactly doing that. It's like computing the local geometry of your space, like the local orientability, and meaning all possible orientations of your space and so on. It's like you know, very simply the tangent graph or like this kind of thing, right? When I put one, that in some sense is like probing the space everywhere. You know, at least it gives you a number of how many directions can you travel from your point away, right? That's computed like this. If I put the number 2 right now, that at least the cardinality of that is directly computed from the cardinality of the first one, because that's just all the possible ways in which you can make lists of length 2 out of the number of elements you had in this first one, right? So in a way, the reason I made this definition originally is that that's analogous to geometry, where the way you build higher multivectors is by wedging lower multivectors, right? So I thought that, you know, analogously, okay, let's just combinatorially take tuples together and that's it. But maybe we need to be a bit more refined than that. And I think crucially we should be, because, you know, if we are to take seriously the fact that space is represented, connectivity of space is represented by hyperedges, we should probably be using the local hyperedge structure to compute those things, right? But
At
anyway,
least you have
Yeah.
always have a dedicated point in the form of a vertex, not an edge place, right?
say it
you
again.
always-
I missed the first couple words.
I mean, you always have this dedicated vertex, which is the part of your an edge vertex vector or a bivector.
Yes.
The vertex is like a dedicated part of it. So
Yes.
if you wedge them together, you essentially wedging only the edge places, keeping the
Yes.
vertex intact. So that's like that represents the point on your manifold or whatever.
Yes.
Yeah.
So that I agree. It's completely analogous to that. You're like doing some operation with the space around the point, where the point is being held fixed, and that's why, you know, the wedge product is what is called a pointwise operation. That it acts on every tangent space around your manifold. It's not. It doesn't have to use any differential calculus to be defined. It's just purely based on kind of the geometric combinatorics of the place, which is like just linear algebra. It's just doing the basic operations of algebra. Okay, good. I mean, it's good to identify. I'm glad that we had this session, and I could clearly see I think the problem is very well formulated now, and so it is much better for me to go after it with this. Yeah. Anyway, any final thoughts?
Formulating of the problem is a huge success in my books.
Yeah.
If you can formulate a problem correctly, then you're halfway there.
Absolutely. Well, mathematicians will tell you that if you formulate the problem well enough, it's already solved. So anyway, at least that's my philosophy. I like problems that solve themselves. So I think that's the summary is here. We previously had a multivector definition that was in a specific to local edge structure, and then what I'm suggesting here is we should define a multivector construction that is sensitive to local edge structure, and hopefully that will lead into a natural notion of shape integration, meaning, you know, same way that we do sort of path integration into curves, we can have sort of bivector integrations into surfaces and things like that, right? So yeah, and that's basically one of the bottlenecks right now. There's a lot of future development depends on this, and in a sense, like if we get this right, I feel like everything is going to fall into place, if there is such a thing as infrageometry to be developed here. So yeah, cool stuff. Thank you very much, guys. That was super helpful for me.
Okay, sounds good.
Ernie.
We have another live stream tomorrow, I believe. Yeah, so tune in for that. It's a guest presentation, which is looking to be quite exciting. So we'll see you then.
All right.
Very nice.
Yeah.
Wonderful.
Bye for now.
Thanks.